Welcome to geometry class. We're talking about trapezoids and kites. Trapezoids and kites are both quadrilaterals. They're special quadrilaterals. A little bit different than parallelograms and some of the other things we've looked at in prior lessons. So let's get into it. What is a trapezoid, first of all? A trapezoid is a quadrilateral with exactly one pair of parallel sides. Here are some examples. You can see here, we've got an indication of parallel sides. And you'll also notice that these sides do not appear to be parallel. These sides across here. And in fact, if we look at this sort of based on appearances, we can be pretty sure that these are not parallel. In fact, we can see that they would actually intersect up here somewhere. Same thing with these sides down here. If you extended these sides up, you can see that they would intersect up above the trapezoid. What about this one? Based on appearances, again, you can see that these sides are parallel. These sides, this top and bottom side, so to speak, are not parallel. You can see that they would intersect off on the left someplace. So that is a trapezoid. Here's another trapezoid. One pair of parallel sides and two other sides that are not parallel. You can see those would intersect. Another trapezoid. Notice here that sometimes we sort of get stuck in a paradigm where the trapezoid is always upright, quote unquote. And that's not the case in geometry. Of course, there is no up, down, left, right. So here you can see that the parallel sides are here and here. Still a trapezoid. This is not a trapezoid. That's a triangle. Definitely not a trapezoid. It's not a quadrilateral, first of all, so it couldn't possibly be a trapezoid. Also, it doesn't have any parallel sides. See, there's no parallel sides in here anywhere, so definitely not a trapezoid. It's a triangle. Is this a trapezoid? Well, it seems to have a pair of parallel sides here, but it also seems to have another pair of parallel sides here. Not a trapezoid. Why is that not a trapezoid? Because the trapezoid has exactly one pair of parallel sides. So that's a parallelogram, not a trapezoid. Which means, by the way, that those two categories of quadrilateral, trapezoid and parallelogram, are mutually exclusive. How about this one? This is actually a rhombus, which means, if nothing else, that it's also a parallelogram, and therefore it cannot be a trapezoid. Not a trapezoid. This looks like a square. Squares are not trapezoids. They can't be because squares are parallelograms, and parallelograms have two pairs of parallel sides, whereas a trapezoid has exactly one pair of parallel sides. Rectangles. Are rectangles trapezoids? No, never. They can't be, for all the same reason. What about this? This is a trapezoid. Okay, it has one pair of parallel sides, and it has one pair of non-parallel sides, and so therefore that is a trapezoid. So again, real quick, we have trapezoid, 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 not a trapezoid, not a trapezoid. Those are not trapezoids either. Okay. Properties of trapezoids. Let's talk about that. First of all, the parallel sides of a trapezoid are called its bases. The non-parallel sides are always called legs. And the two angles that have a base in common are called base angles. Two angles that have a leg in common are supplementary. Notice they're same side interior angles. Let's look at some examples. So in this diagram, this is a base, and this is a base. This is a leg, and a leg. These are one pair of base angles, and these are another pair of base angles. Notice every trapezoid has two pairs of base angles. That's kind of strange. Talk about an isosceles triangle. There's usually one pair of base angles, but in trapezoids, there's always two pairs of base angles. And notice that here, we have these angles that are supplementary, and these angles here that are supplementary. And that's because, again, they are same side interior angles. Two lines which we call bases, and a single leg is, of course, a transversal, and so those are same side interior, and therefore they're supplementary. How about over here? Where are the bases? Well, we have one base here, one base here, and we have two legs. We have four base angles. There's one pair. Here's the other pair. And of course, we know that these angles are supplementary and these angles are supplementary. Let me just pause and say that in these diagrams, I have not taken the time to indicate parallel sides. We've sort of been working based on appearances, and that's a little bit dangerous. It's not something we normally do. So just be aware that it's happening. Typically, if I gave you a diagram just like this and asked, is that a trapezoid, you'd have to ask the question, I don't know, are those sides parallel? And if the answer to that is no, then it's not a trapezoid. And if the answer to that is yes, then it's a trapezoid. Same thing over here. We have two bases. That's a base. This is a base. We have a leg, we have a leg, we have a pair of base angles here, we have a pair of base angles here, and of course we have supplementary angles here and supplementary angles here. So those are some very general characteristics that you need to know about trapezoids. The next thing we need to talk about is what's called an isosceles trapezoid. An isosceles trapezoid is a trapezoid with congruent, non-parallel opposite sides. Okay, that's a little bit of a mouthful. What am I talking about? Well, by definition, every trapezoid has two parallel bases. We know that. An isosceles trapezoid is one where these non-parallel sides are congruent. Okay, so we have parallel sides and congruent sides in an isosceles trapezoid. Talk about the isosceles trapezoid angles theorem. It says the base angles of an isosceles trapezoid are congruent. So that says that these base angles are congruent. Let's see if we can prove that. We'll just start with this isosceles trapezoid. You'll notice that if this trapezoid exists, there must be some line that exists right here, which is parallel to this one over here. That line exists somewhere. Okay, we know that it exists. It goes from this vertex here. We'll call that A. It goes from A to this point E. If you look carefully, there's a parallelogram right here. It's parallelogram ABCE. And because we know certain things about parallelograms, we can be sure that AE is congruent to BC because AE and BC are opposite sides of a parallelogram. We know that parallelograms' opposite sides are always congruent. So AE is congruent to BC, and so by the transitive property, AE is congruent to AD. And so we now see that we actually have here, we've established an isosceles triangle. Well, we know there's something called the isosceles triangle theorem, which says that the base angles of an isosceles triangle are congruent. And we also can see, if we look here at angle AED and BCE, those two angles, if you look at parallel sides here and a transversal here, those two angles are corresponding angles, and therefore by the corresponding angles postulate are congruent. And you can see again by the transitive property that if this angle ADE is congruent to AED, and that's congruent to BCE, then this angle D is congruent to this angle C. So there's the proof of the isosceles trapezoid angles theorem. The next theorem we need to talk about is the isosceles trapezoid diagonals theorem. Simply says that the diagonals of an isosceles trapezoid are congruent, and we can look at that as well. So here we have an isosceles trapezoid. We can draw in the diagonals. In order to prove the theorem, let's just break this into two triangles. We have trapezoid ABCD. It's isosceles. We can see that. Let's break this into triangle ACD, and we'll break it into triangle BDC. There we go. Okay, so this over here on the left is A, C, D, and on the right we have B, D, C. So let's just identify some points of congruence here. We know that AD is congruent to BC. That's given up in the diagram. So AD is congruent to BC. We also know in an isosceles trapezoid, by the theorem we just looked at, that this angle over here, angle D or vertex D, is congruent to vertex C. Those are base angles in the trapezoid. And then we know that DC is congruent to itself by the reflexive property. So you can see pretty quickly we have by side angle side in both of these triangles, we have congruence. And CPCTC tells us that this must be congruent to this, corresponding parts of congruent triangles. So we can see that diagonal BD is congruent to diagonal AC in an isosceles trapezoid. Next type of quadrilateral we need to talk about are called kites. First of all, we should probably define a kite. A kite is a quadrilateral with each side congruent to exactly one adjacent side. Each side congruent to exactly one adjacent side. Here is a picture of a kite, and you'll notice some things about it. First of all, this side is congruent to this side only. Each side is congruent to exactly one adjacent side. So every side has two adjacent sides, and it will only be congruent to one of those adjacent sides. So this side is congruent to this one, but not to this one. This side is congruent to this side over here, but not to this one down here. And the same analysis applies down here. So you can see we have two pairs of congruent sides. The difference between a kite and a parallelogram is, in a kite, the congruent sides are adjacent, whereas in a parallelogram, they're opposite. In other words, if I could say that differently, if we took this long side down here and switched it for the short side up here, we would actually form a parallelogram. This side would come down here, and then it would come across here, the shorter side. So that's a kite. It is mutually exclusive. It is distinct. It is always different than a parallelogram. You can never have a kite that is a parallelogram. You cannot have a parallelogram that is a kite. Notice one thing about the kite. If we move this vertex up, it's still a kite. Notice when we get to about here, it actually looks like a parallelogram. And so at some point in time, as we move this vertex and form these different but related kites, you'll hit a point where it actually becomes a parallelogram. Only one point. And of course, if you keep going upward, you can see that it's a kite again, because even though now these bottom sides are shorter, they're different in length than the top two sides, and so it's still a kite. A lot of different varieties on the shapes of kites. The key is to make sure you have two distinct pairs of adjacent congruent sides. I mentioned already that a kite is a special quadrilateral, but it is not a parallelogram. It's never a parallelogram. It will never be a parallelogram, nor, by the way, is it a trapezoid. Kites and trapezoids are separate and distinct. Trapezoids and parallelograms are separate and distinct. Kites and parallelograms are separate and distinct. The Kite Theorem says the diagonals of a kite are perpendicular. So if we have a kite and we draw in the diagonals, they will always be perpendicular. Let's just prove this theorem real quick. To do that, I'll just start by drawing a kite. And what do we know about the kite? We know that these two sides are congruent and these two sides are congruent. In the proof, I'll just draw in this diagonal. There we go. It's not perfect, but I think you get the idea. And you can already see that these two triangles that I've created by drawing in the diagonal are congruent. Hopefully you can see that by side, side, side. This is congruent to itself by the reflexive property. So by side, 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 I've already got congruent triangles. Well, CPCTC tells us that this angle is congruent to this angle, and this angle is congruent to that angle there. So now if we go ahead and draw in the other diagonal, there it is right there, and we focus on this top half up here, we can see that we have two other congruent triangles here. We'll call that triangle ABE and triangle CBE. Well, those triangles are also congruent, and you can see they're congruent by side angle side, the reflexive property in here on this little segment, which is segment BE. So triangle ABE is congruent to CBE, triangle CBE. And so then by CPCTC, again, we end up with these angles here. I'll draw in 3 arcs on each side. Congruent. In addition to there being congruent angles, they're also a linear pair. And every time you have two congruent angles that are a linear pair, which means they're supplementary, you know their measures must be 90 degrees. So instead of these congruence marks, we can come in here and just go ahead and say that these are actually right angles, which proves the theorem that the diagonals of a kite are perpendicular to each other. Okay. You may notice also, if you pay attention, by CPCTC we can conclude that this segment here, AE, is congruent to EC over here, and so you'll find that one of the diagonals bisects the other diagonal, but unlike in a parallelogram, they don't both bisect each other. Those are the things we need to review about kites. We talked about trapezoids. Make sure you look at the rules. Make sure you try to apply them on a few problems on your own. If you have any questions, send me an email.